Hello, wonderful people. Welcome to Cosmology Talks and Cosmology from Home. This is another talk in a series of talks on the spectacular new sample of supernova from the Dark Energy Survey. This one is about using the supernova as a rung in the inverse distance ladder, which is essentially, instead of calibrating the luminosity of supernova using things we know about that are near to us and climbing out to greater distances, they will calibrate them using things we know that are far from us, and they climb back down. The not so spoiler result is that the two ladders converge on different values, in other words, the Hubble tension. In the era of the Hubble tension being 5 sigma, it's hard to oversell how illuminating the inverse distance ladder is regarding what can and cannot solve the tension. Firstly, it can be constructed more or less without the CMB, meaning the early universe ΛCDM value doesn't rely on any CMB measurement systematics. But most relevantly for today's talk, when one adds supernova as the last rung, it also more or less kills the chances of any low redshift change in the expansion history of the universe being able to explain the tension. And we'll see why in the talk. This talk will be discussed during Cosmology from Home this year in the extended themed discussion session on the Dark Energy Survey supernova and their cosmological implications. So if you want to join that discussion or even just watch it, you should sign up for Cosmology from Home via the link in the description. In this talk, we have Ryan Camilleri, who is a PhD student at the University of Queensland, and Tamara Davis, who is a professor at the University of Queensland. So no more waiting, let's climb on the ladder. Ryan, Tamara, do you want to start by telling us briefly about your paper?
We've performed a measurement of the current day expansion rate using the inverse distance ladder. I guess we'll get into a little bit about what the inverse distance ladder is, but you may have heard about the Hubble tension. So performing different measurements on the current day expansion rate is really important for cosmology.
Okay, cool. If people are thinking of this talk or your paper 6 months or a year from now and they only remember two things, what would you like those two things to be?
The improvement in the constraining power from these new state-of-the-art data sets from both the Dark Energy Survey and DESI. It really highlights the importance of continually improving on the data sets that we have going forward. And secondly, so we get a H naught that is about 67, which is in agreement with the Planck result. However, we do get a varying expansion rate at about a redshift of 0.5. I think that's interesting and worth exploring further in future analysis.
Do you want to go into some of the background about the inverse distance ladder now? How is it built? What does it tell us in principle? And then we can find out precisely what you found with the supernova added to the ladder.
First, I'll give a bit of a background on why we want to measure the Hubble constant. So you may have heard of a bit of a tension that we have or when we measure the current day expansion rate. This is a tension between early time and late time probes. So on the plot on the bottom here, we have the Planck constraint in pink, as well as the Shoes constraint in blue. And you can see that we get this about 4.9 sigma tension between their constraints. And we've also overlaid a few of the other constraints in the literature that still see this tension as well. So this may indicate that we're using the wrong cosmological model or imply that there's new physics, or it may be due to unknown systematics with a particular measurement. So we want to try and find ways to kind of isolate or provide independent measurements that may uncover the truth about what's happening here. So firstly, what do I mean by just the normal distance ladder? So when we do cosmology with supernovae, we have a degeneracy between two of the key cosmological parameters. First, the current day expansion rate, H naught, which is what we're interested in, as well as the absolute magnitude of the supernova, so how bright the explosion is. And I guess a really intuitive way to understand what's happening with this degeneracy is by looking at the Hubble diagram. So on the top left plot here, we have, in particular, the top panel, we have the distance modulus versus redshift. We've also got a couple of different models overlaid there. So if we have a H naught value that is higher than what we expect, then essentially things are further away. The current day expansion is faster and things are further away. So these overlaid models, our predictions are shifted up, and the inverse is true if H naught is less. Likewise, if we look at the data points here from the supernova, if the absolute magnitude is brighter, then that would shift the data points down. And if it was dimmer, then that would actually shift these points up.
So why is it when it's brighter it goes down exactly?
It's just because this is a magnitude scale and lower numbers are brighter on the magnitude scale.
Cool. And the reason why this is important, I guess, is that the supernovae aren't standard candles, but standardizable candles. Like if we did know that every single supernova went off with exactly the same brightness, there wouldn't be, I mean, there would be this degeneracy, but it wouldn't be relevant because MB would just be one number for every single supernova.
Well, actually, no, that you still have this problem even in that case because we still need to know what MB is.
Okay, but if our stellar models were perfect, then...
Yeah, so if we knew exactly what MB was, if we know exactly how bright they are, then this wouldn't be a problem. We would just be able to directly measure H naught. But because we do not know exactly how bright the supernovae are, we have to calibrate that some way. And often that's done at low redshift with things like Cepheids or tip of the red giant branch or surface brightness fluctuations, etc., etc. And in this inverse distance ladder technique, as we'll see, we're doing a calibration not at low redshift, but at high redshift.
Typically, this calibration is done using low redshift data. So we start off with parallax measurements to Cepheids. This calibrates the Cepheids, and then we use the Cepheids measurements to then calibrate type 1a supernova. However, for the inverse distance ladder, we do the inverse, and we start at the very early universe at the cosmic microwave background. So what we do is we use a prior on the sound horizon scale, RD here, and this is at the drag epoch. We don't take all the information from the cosmic microwave background. We just take this prior on this parameter, and we use that to set a scale on the baryonic acoustic oscillations. We can then get absolute distance measurements to the baryonic acoustic oscillations, and this allows us to calibrate the supernovae using the inverse distance ladder.
Yeah, so in essence, we're anchoring the Hubble diagram at high redshift instead of anchoring at low redshift, and then using the supernovae to define the expansion history from that high redshift and see where it hits the axis at low redshift to figure out what H naught is.
So in some sense, the same way that you use a Cepheid to say, okay, that supernova was actually this far away, therefore I know how bright it was, you're now saying, okay, BAO at that redshift was this value, therefore I know that distance, and this supernova was also at this redshift, so I know how far away it was, and therefore I know its intrinsic brightness.
Exactly. However, we do still need a model to, one, trace back to redshift of 0, where we are now, and also to join the data sets of the different redshift ranges. So what we use is cosmography. So this is a purely kinematic model and essentially a Taylor expansion of the luminosity distance. So it makes no assumptions about the energy contents of the universe, but it does retain the assumption of homogeneity and isotropy. And one of the questions we have to ask ourselves is, what is the optimal order of expansion? This is something that we look into as well, but it's not the primary result of the work, but we do look in this as well. So this brings us to the data that we use. So we use the 1829 likely type 1a supernova from the Dark Energy Survey. On the right, you have the Hubble diagram. And this is a state-of-the-art supernova sample that's increased the number of supernovae above a redshift of 0.5 by a factor of 5. We also combine this with 12 BAO measurements in 7 different redshift bins from the DESI collaboration. And these were determined from over 6 million extragalactic objects. So that brings us to our key result. We find H naught of 67.19. So this is compatible with other inverse distance ladder measurements. You can see those in the plot on the bottom in green on the top panel, as well as the measurement with Planck. And this might not be surprising as Planck was used to calibrate the baryonic acoustic oscillations. We also find that our result has 50% smaller uncertainties than what was found using in Macaulay et al. In 2019, and they used the DES 3-year supernova sample along with SDSS. Interestingly, though, we do find that we do have a different expansion history than Planck at about a redshift of 0.5. So here we have 2 different plots that show the expansion history, just with different scales. So at the top right, we have the overlaid 4 of the DESI BAO measurements in red, as well as the supernova data in pink. The measurements with error bars are binned supernova measurements. And you can see that we have this at about redshift 0.5, this different expansion histories, even given the scale which was set by Planck of the BAO. In the bottom, we then look at the DESI BAO expansion history on its own, and we also see the same feature. So at about redshift 0.5, it's differing from Planck, but it agrees with our expansion history when we combine it with the supernova. What we do find as well is that the supernova prefers a higher H naught value.
Yeah, so this results is sort of intriguing because we end up with an H naught that's close to Planck, but the expansion history to get there that's preferred by the BAO and supernovae is slightly different. So in some ways, it's almost a bit of a coincidence, but it does, like, you can see just how far you would have to move the calibration scale to move up and get an H naught of near like 73, because that's on that vertical scale of the top plot. And so the calibration from the BAO would have to shift quite substantially or the expansion history would have to do some massive sweep upwards in order to hit that value.
Right at the last minute as well, because the supernovae, when anchored to the BAO, are getting to quite low redshifts. What is this really weird one supernova bin that's like a...
Well, that's just a bin in which there's not a lot of data that's between the high and low redshift samples.
Ah, I see. Yeah, that makes sense.
Yeah, so depending on exactly what binning you use, you don't necessarily always see that sort of small bin with a bit of deviation.
Yeah, it does have a way bigger error bar than all the others. So if I can understand this correctly, the blue curve in the top right-hand corner is the data in this fourth order of cosmography fitted to all of the data points, the DESI and the DES ones, but not fitted to Planck, just using the one sound horizon value. And then the black curve is the lambda CDM prediction as a function of redshift from Planck alone.
Yes, exactly right.
And yeah, okay. Now let's go to the bottom left-hand one. Again, the black curve here is Planck. It's the same thing. And okay, now the blue and the red are the supernova and the BAO fitted separately.
The blue is still the same blue curve as the previous plot, so it's supernova and BAO, and the red is just the BAO on its own.
Are the supernova the thing pushing this up, or is it the BAO pushing it up? Like, would supernova on their own?
From this, like the BAO on its own deviates in its expansion at this redshift. What the supernova is doing is driving H naught up a little bit as well at the lower redshift range. So you can see the red kind of hits the y-axis at a lower value there.
So this actually gives me, and I segue into the other question I wanted to ask is, on your previous slide, you said, okay, the H naught value is this. BAA groups are able to quote a very similar like error to this, not even looking at supernovae. So what is it that the supernova are actually adding?
The supernova is adding the constraint on the expansion history on that redshift range from about 1 to about 0.01. You can see in the plot here that the uncertainties on the BAO alone are a little bit wider, and the blue expansion history in that low redshift range is quite tight.
The other question I want to ask is, like, is this deviation at redshift 0.5, is this highly correlated to the preference for evolving dark energy BAO and DESI are seeing? Is that like just another way of seeing that same information?
Yes, exactly right.
Yeah, the fact that the expansion histories from the best fit BAO and supernovae differ slightly from the expansion history from the CMB is exactly what we're seeing when we're doing fits for the cosmology, where we're seeing potentially time varying dark energy or something that deviates from the flat lambda CDM model, because that black line there is the flat lambda CDM model.
Yeah, so this is like a cool way of seeing the same thing from a slightly different perspective to, like, when you're training your mind about trying to look for what model might fit it, keep this curve in mind as well, I guess.
Yeah.
So when DESI provides its H0 constraints using flat lambda CDM, they don't actually provide a constraint just using the DESI BAO alone. So when they combine with the CMB, they get a little bit of a smaller constraint. Well, they get a smaller constraint than what we have here of about 0.38. So they do provide a similar measurement of H0 using just priors from the CMB. Some of them are using the same or particular slightly different priors, and they get statistical uncertainties about 0.8.
And on this previous slide, remind me, like that is flat lambda CDM H0, not fourth order cosmography H0.
No, this is fourth order cosmography. Yeah, so we only provide constraints using the fourth order cosmography. That's our key results. Yeah,
that is beyond lambda CDM, because you're allowing.
I guess we want to be agnostic about the choice of cosmological model as much as possible.
Yeah, so rather than fitting a whole cosmological model, including dark energy, dark matter, etc., and H0 simultaneously, which is what's done with the BAO typically, this is using the shape preferred by the supernova data combined with the BAO data to figure out where we hit the H naught at the low redshift.
There is no equivalent BAO number published to this, I guess, because when they assume flat land into CDM, they've got far fewer free parameters, so you expect them to have narrow error bars. So it's hard to make the direct comparison.
Yeah, so they don't use a direct comparison to this. Yeah.
No, DESI does do some different calibrations of the sound scale that are independent of the CMB and compare all of their models with that as well. So there's a lot done in the DESI paper.
But if they assume flat lambda CDM, they don't have as much freedom, which presumably narrows the error bars.
Well, they fit to the not flat lambda CDM as well.
They don't use cosmography?
No, but they fit W not WA, obviously, because that's one of their main results.
Hi, me from editing here. When we discussed this while recording, I was getting a bit confused about exactly what the supernova added to the inverse distance ladder, and it mostly got cleared up during the discussion, but I want to express it now quickly as clearly as I can. My confusion came from the fact that the DESI quote similar uncertainties in their own H0 measurements without supernova included to what Ryan and Tamara are quoting here. So what have the supernova added? Is it just 0.1 kilometers per second per megaparsec in precision? But it isn't. The resolution is that the DESI constraints of equal precision to what's being quoted here assume lambda CDM, whereas Ryan and Tamara are quoting H0 in the fourth order cosmographic parameterization, which has much more freedom for how the Hubble parameter can change over time. DESI unfortunately don't quote their results for the same tomographic expansion without supernova, so it's hard to do an apples to apples comparison to the result on the screen at the moment. You could read it off the figure, but that's not that satisfying. Thankfully, DESI do include the dark energy survey supernova in their own model constraints, for example with evolving dark energy, and that is very illuminating. Here, in the table on the screen, one can see that if one ignores the supernova and constrains the W0 WA model, allowing spatial curvature as well, the uncertainty on the H0 constraints explode to as big as plus 2.6 minus 3.5 kilometers per second per megaparsec. However, when you add the dark energy survey supernova back into the ladder, the constraints collapse again right back to the usual 67-ish plus or minus 0.7-ish. So the supernova really do take care of that last rung on the ladder, taking you from the BAO scales to almost zero, which is what Ryan answered me in the talk when I said, what are they adding? He said they're constraining the expansion history after the BAO scales, but now it's kind of just sunk in properly. So no matter what you try to do between the BAO scales and Z equals 0, you could have evolving dark energy, cosmography, spatial curvature, you're going to end up with H0 as 67 plus or minus 0.7 when you add the supernova in. And this is why the inverse distance ladder has such a strong message for the Hubble tension. You essentially can't fix the Hubble tension with something happening between the BAO scales of Z of about 2.5 and the lowest redshift supernova. I guess this was known in the past, and you can see it in the Macaulay et al. Result, but this new data just makes it worse. The statistical error has shrunk, but also the systematics are much more under control in this dark energy survey supernova catalogue. It's a real puzzle. Cool. Yeah, so where do we go next? How can we improve this distance ladder? I guess maybe there's more DESI data coming soon, which will narrow those red ones, but are there calibration steps that can improve the kind of merging of the data sets, or?
I guess it just motivates the continual need for improved data sets. And also, going forward, we could also, instead of step away from the inverse distance ladder and calibrate the DES supernova data using, tip of the red giant branch.
In some sense, this plot you've got on the screen at the moment, it shows so clearly why the Hubble tension is so hard to fix, because we've constrained the redshift evolution from 2.5 to I don't know 0.1, 0.05, and there's not that much range to shift it. It's either something happening extraordinarily locally, or it's above redshift 2.5. But then the CMB is fitting lambda CDM so well that it just shows why it's so hard to fit. You can't just fiddle with supernova.
I think this is a really nice demonstration of exactly that. That the difference you would need in the calibration to get something that's as high as a H0 of 73 is really quite dramatic. It's hard to imagine how that could happen. So we're seeing visually what a 5 sigma result looks like.
Could one, if one's putting one's crazy theorist hat on, is there a window between 0.3 and where that one data point is that is so unconstraining? to just put in like a super exotic dark energy model right there?
Not really, because there's actually, if you zoom in on the, and we maybe should put this on a log plot, because if you zoom in, there are data points at lower redshift than that. Yeah, a blip that goes up and down wouldn't help. You would need to have it stay up for those like really low redshift data points to be up as well. And just to be really clear, this isn't saying that, you know, Cepheid calibrations or anything like that are wrong. It's just confirming that if you calibrate to the standard rulers and the sound horizon scale with BAO and CMB, the supernovae give you information of the expansion history at low redshift, and it can't be dramatic enough to fix this tension. So it's not saying that the low redshift calibrations are wrong. It's just another way of showing that there is that tension there.
Something's wrong.
Yeah, something weird is happening.
Okay, cool. Yeah, let's wrap up now. And what work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
I think that's something that's really underappreciated by the community. Investigations into the statistics of model comparisons and tension metrics that we use, as well as the impact that our priors have on our results. So this is like a lot of this work is really heavily statistical, and it can really be hard to get your head around that. So a lot of the work that's going into that really helps, and I think it's as we get more and more improved data, I think those statistics are becoming more and more important.
Mm-hmm, mm-hmm. And it's so important in cosmology as well, because we only have the one universe. Like, experimental sciences can be a bit more lazy about statistics, because if they make statistical biases, they just take more data, and then eventually that bias will fade away. But we can't. Like, we've got all of these large scale CMB problems that are just going to sit there and never be solved, because we don't get to make 10 more or 1,000 more large scale CMBs. So these axes of evil and hemispherical power asymmetries and all of these things are just, yeah. So it's super important that we're more rigorous as cosmologists, because we don't have the advantage of taking more data. So yeah, I totally agree with that. Awesome. Thanks everyone for watching. If you like this, please subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and for the channel, because YouTube will know to recommend more stuff like this to you. And share the channel with colleagues. If you have any questions or comments or suggestions, leave a comment. Otherwise, check out one of the other recent Dark Energy Survey talks. There's lots of great ones that we've just been released. And thanks, Ryan and Tamara, for the great talk.
Thanks for having us.
Thanks for having us.